So we continue with the example. A uniform beam XY of length 8 meters and weight 40 newtons sits on two supports A and B, 1 meter each from X and Y respectively. Weight of 18 newton and 60 newton are placed at X and Y respectively. Draw the force diagram and find the reactions at A and B. So we are going to do this. Solution. We have a uniform beam. Now take note, the beam is uniform. So it means that the weight of the beam is going to act through the middle of what? The beam. So let's do this. This is my beam. Extend this a bit. The beam is X and Y, and the length is 8 meters, and weight 40 newton. So the weight of the beam is going to pass through the middle of the beam. (40 newton). Sits on two supports A and B, 1 meters each from X and Y. So we're going to have a support here, a knife edge, which is 1 meters from X, and we have another here which is also 1 meters from Y. Then we have weight of 18 newton and 60 newton placed at X and Y. So there's going to be a weight here, or a force. This is 18 newton. Then we have another force placed here, which is 60 newton. So we have to draw the force diagram. This is the force diagram that we have just drawn. Then we are asked to find the reactions at A and B. So this is pivot A and this is pivot B. Then the reaction, or support A and B, the reaction at A is R1 and the reaction at B is R2. You can use any letters for this if you wish to. Now, we are not done with the force diagram because we have to get the distance between this and this. Now, remember that the beam is 8 meters long. So halfway through this is, from here to here, is 4 meters. So it means that, now let's call this place P. So I can say SP is 4 meters. Then AP will be 4 minus 1. That is 3 meters. And also PY is 4 meters, BY is 1 meter, then PY will be, PB will be PY minus BY. So we also have 3 meters. So this is the force diagram. Now we can look for the reactions at A and B now by doing this. First of all, we have to take a look at this. We know that for the system to be in equilibrium, the total upward forces must be equal to the total downward forces. So the upward forces are the reactions, while the downward forces are this weight, the weight of the beam, and this other weight, 60 newton. So therefore, we have upward forces equals to downward forces. So we have R1 plus R2 equals 80 plus 40 plus 60. That's going to give us 180 newton. Now let's take moment. about, now you can take moment about point A or point B. You are going to get the same result. So if I take moment about point A, the moment about A becomes 0. The moment due to R1 about point A is 0 because there is no perpendicular distance between R1 and what? A. So we can trace out the moment. Now since we are taking moment about this, now let's look at all the forces. R1, so this, the moment of this is already 0. So we'll check the moment, direction of the moment of this, and this. Now taking moment about this, assuming this force is not there, this beam will try to, because of the direction is downward this way, we try to rotate the beam in this direction, and this is the anti-clockwise direction. Now if you look at this other force here, assuming this is not there, this is not there, and this is not there, this force will tend to rotate this in this direction. So this is clockwise direction. Then we'll go to this. Same goes to this. Because we are taking moment about this, remember that when we are taking moment about this one will not be there, and we have this not there, this other force not there, and this not there. This beam is going to this force is going to rotate this beam about this point in this direction. So we have clockwise moment. Then we'll go to this last force here. We'll take moment about this force is not there, this is not there, this is not there. This force is upward, so it's going to rotate this beam about this point in this direction. So this is anti-clockwise moment. So we know that for the object to be in equilibrium, we know that clockwise moment is equal to anti-clockwise moment. So let's get the clockwise moment. So we'll start with this clockwise moment. The force there is 40 Newton. Then the distance between the 40 Newton and the pivot A is 3 meters. So we have 40 times 3 plus, then we have this force which is clockwise, and the distance between this and this is 60 times, now the distance is 1 plus 3 plus 3. We have 1 plus 3 plus 3. So we have 1 plus 3 plus 3. That is all for the clockwise moment. Equal to, now we look at the anti-clockwise moment. We have 80. The distance between this and this is just 1 times 1 plus the other anti-clockwise moment is this. The distance is, or the force is R2 times, and the distance is what? 3 plus 3. So that's going to give us 120 plus 60 times 7 equals 80 plus 6R2. So we're going to have the 60 times 7. So I'm going to have a 120 plus 60 times 7 is 420 equals 80 plus 6R2. So we have 40, 120 plus 420. That will give us 540 equals 80 plus 6R2. So I'm going to have a 6R2 equals 540 minus 80. So 540 minus 80 is equal to 460. So we have 6R2 equals 460. Equals 460. Now 6R2 equals 460. Divide both sides by 6. So that will give us R2 equals 76.666667 to 2 decimal places Newton. Now we can go back to look for R1. We know from the first equation that R1 plus R2 equals 180 Newton. So substitute 76.67 Newton for R2 into the above equation. So we're going to have R1 plus 76.67 equals 180. So R1 equals 180 minus 76.67. 180 minus 76.67. So we're going to have R1 equals 103.33 Newton. So therefore, the reactions at A and B are 103.33 Newton and 76.67 Newton. All right, thank you. See you next time.